My name is Ashley Clarviratin from grade 12 Demeter, and today I'm going to discuss the cosmic distance ladder. The cosmic distance ladder is like a giant ruler used to measure the distances in the universe. Think of it as a ladder because it's built step by step, with each method relying on the previous one. At the bottom of the ladder is parallax, which measure distances to nearby stars by observing their apparent shift against the background as Earth orbits the Sun. Once we know the distance to nearby stars, we can use them as reference points for the next step. Further up, we have variable stars like Cepheus and RRD rays. By comparing their intrinsic brightness to their apparent brightness, we can determine how far away they are. Even farther up, we use globular clusters, dense group of stars, to measure distances. By studying the stars within them, particularly the brightness and color, we can estimate their distances. By climbing this ladder of methods, astronomers can confidently determine distances to objects in space.
Galactic distance ladder is a method used by intrepid travelers to measure distances to faraway celestial objects. The first rung of this ladder are objects which rely on seeing how nearby stars move against the background of space. Using these measurements over time, the actual distances can be calculated. The next rung is made of stars called Cepheids. Cepheid variables flicker and change at a rate which is intrinsically tied to the brightness. All our travelers have to do is measure how quickly a Cepheid brightens and dims to calculate their actual brightness, and therefore their distance. These stars act as our rungs to travel further and further into the darkness of the universe. But there is a limit to these stars. As they get further away, we cannot see them without our telescopes, so even brighter celestial objects need to be used. One of these is the Type 1a supernova. These stars are explosions of white dwarfs and can be seen to distances of around 10 billion light-years away. The last rung in our ladder is redshift. By measuring how galaxies are moving away or towards us and their respective speed, the distances to some of the most early known galaxies can be found, shining through the dark, signaling from 13 billion light-years away.
I'm Cesar Miguel Buena, and I'm here to explain how light years work. So a light year is a unit of distance used in astronomy, measuring how far light travels in 1 year through a vacuum. Light moves at about 186,282 miles per second. So in 1 year, it covers about 1.88 trillion miles. Astronomers use light years to describe vast distance between stars, galaxies, and other celestial objects. Because space is incredibly vast and regular units like miles or kilometers become impractical over such immense scale.
You may have heard about a unit of measurement called light years, but what exactly is a light year? Essentially, it measures the distance that light can travel in 1 year, which is an incredibly long way, 9,500,000,000,000 kilometers in fact. Measurements of distances between objects in space are often calculated in light years or parsecs, which are the equivalent of 3.3 light years. Earth is 4.24 light years away from Proxima Centauri, the next nearest star after our Sun, while the Milky Way galaxy is approximately 150,000 light-years across. To put this in context, we are just 0.000015 light-years from our own Sun. But why do things this way? First, light is convenient. Throughout the universe, all light travels at exactly the same speed, about 300,000 kilometers per second. We don't usually think about light traveling anywhere because when we flick on a light switch, there it is. We don't have to wait for the room to light up. It happens instantaneously, except that it's not instantaneous, it's just insanely fast. In fact, let's pause for a second and reflect on how ridiculously quick the speed of light is. If you could travel at the speed of light, you could circle the globe of Earth almost 8 times in 1 second. A light beam needs only 8 minutes to travel the 150 million kilometers from the Sun to the Earth. The main reason for using light years, however, is because the distances we deal with in space are immense. If we stick to miles or kilometers, we quickly run into unwieldy numbers just measuring the distance. Using a longer yardstick, so to speak, helps keep the numbers at least manageable.
Allowing for tracking and calculation to determine the object. This method is commonly used in astronomy to gauge and other mathematics.
Hi, I'm John Michael Lopez and I'm here to explain the apparent magnitude and the absolute magnitude. Based on the definition, the apparent magnitude is how bright a celestial object appears from Earth. It's influenced by the object's intrinsic brightness, its distance from Earth, and any interference from dust. The scale dates back to Ptolemy, ranking stars from brightest first magnitude to dimmest sixth magnitude. Brighter objects have lower magnitude numbers, while the absolute magnitude reveals a celestial object's true brightness, and regardless of distance, it's what's an object of apparent magnitude would be if it were 10 parsecs, about 32.6 light years away.
Good day everyone, I'm Dice Santos and I'm here to discuss distance modulus. The distance modulus is a crucial concept in astronomy that allows astronomers to determine the distance to celestial objects such as stars, galaxies, and other astronomical bodies. It serves as a method to quantify the brightness of these objects based on their distance from Earth. In astronomy, the apparent magnitude refers to bright an object appears when observed from Earth. The brightness is influenced by both intrinsic luminosity of the object and its distance from us. On the other hand, the absolute magnitude represents the intrinsic brightness of the object, specifically if we're situated at the standard distance of 10 parsecs or 32 light years away from Earth. The distance modulus is calculated by subtracting the absolute magnitude from the apparent magnitude. The mathematical formula distance modulus provides astronomers with a quantitative measure of how much the brightness of an object is affected by its distance from Earth. By comparing the apparent magnitude to the absolute magnitude, astronomers can deduce the distance to the celestial objects. By utilizing distance modulus, astronomers can make accurate distance estimations to various celestial bodies, aiding in the study of the vast cosmos and enhancing our understanding of the universe scales and structure.